Have you ever thought about the sheer power flowing through industrial pipelines? I mean, when that power is under extreme pressure, the line between everything running smoothly and a total catastrophe comes down to a set of incredibly detailed rules. Today, we're going to pull back the curtain on the playbook for high-pressure piping. That's Chapter 9 of the ASME B31.3 code. So, really, what is it that keeps a pipe carrying pressures that could literally level a building from just failing? You might think, oh, just make the pipe thicker. But it's so much more than that. It's a whole system of safety, and that system is exactly what this code is all about. So to really get how this system works, we're going to follow the entire life of a high-pressure pipe. We'll kick things off with the code itself, then we'll dive into picking the right materials, the super critical fabrication process, the exhaustive inspection, and finally, the ultimate proof, the pressure test. Okay, first things first. You have to understand that Chapter 9 isn't just some footnote in a bigger book. Nope. It's basically a self-contained, highly specialized rulebook for situations where failure is simply not an option. We're talking about places like chemical plants or power generation facilities. This framework is all about intense scrutiny at every single stage, from the first drawing to the final sign-off. Nothing, and I mean nothing, is left to chance. So what's the first pillar of this whole safety framework? Well, it all starts at the most basic level you can imagine, the materials themselves. Before a single piece of pipe is ever cut or welded, the code demands absolute proof that the building blocks are tough enough for the job. The code kind of splits materials into two big buckets. On one side, you've got your listed materials. Think of these like trusted, brand-name ingredients you'd use in your kitchen. They're pre-approved with a long track record of performance. Then, on the other side, you have unlisted materials. Now, you can use them, but the burden of proof is totally on you to show through a ton of testing that they meet every single safety requirement the code throws at them. And here's a really crucial point. The code demands more than just strength, the ability to not get pulled apart. It demands toughness. And toughness is all about absorbing energy and resisting fracture, especially when it gets cold and some metals can get really brittle. You want something that will bend, not shatter. So how in the world do you measure something like toughness? Well, check this out. This is a pretty clever method called the Ch9b impact test. Engineers literally cut a tiny notch, a planned weak point, into a metal sample. Then a huge, heavy pendulum smacks right into it. The whole point is to measure how much energy that piece of metal can absorb before it finally breaks. This test is the ultimate proof that the material will deform under stress instead of just shattering like glass. All right, once you've picked out these proven, super tough materials, the next big challenge is joining them all together without creating a single weak link in the chain. And that brings us to fabrication, where, let's be honest, the most critical process of all is welding. Now, welding for these high-pressure systems is this meticulous four-step dance. First, you prepare the pipe ends perfectly. Then, you preheat the whole area to control how it cools down, which prevents cracks. The welding itself? That's only done by qualified welders, following a very specific, pre-tested procedure. You can think of their qualification like a highly specialized driver's license just for this job. And finally, most of these welds go through a post-weld heat treatment to get rid of internal stress and make the joint even better. And this just perfectly shows the insane level of detail in this code. It actually specifies the maximum amount two pipes can be misaligned before you can even think about welding them. We're talking about a gap of less than 1.5 millimeters. That's thinner than a nickel. This kind of precision is what ensures the final joint is one continuous, strong piece with absolutely no built-in weak spots. So you've used the right materials, you've followed this precise fabrication process, you're done, right? Not even close. The next stage is all about inspection, and the philosophy here is simple and powerful. You don't assume the work is perfect, you prove it. And this table right here, this is basically the inspector's Bible. It takes all the guesswork out of the process. It's a systematic playbook that says, hey, if you're looking for this kind of flaw, you have to use this specific method to find it. It's a comprehensive strategy to make sure nothing gets missed. And what this really shows is that you need the right tool for every possible problem. I mean, for a little imperfection on the surface, just looking at it might be enough. But to find the really dangerous stuff, those hidden flaws like an internal crack, the code demands much more powerful tools. Things like radiography, which is basically an X-ray for steel, or ultrasonic testing, which uses sound waves to paint a picture of what's going on deep inside the metal. But just finding a potential imperfection is one thing. The next, absolutely crucial question is it dangerous? Because not every tiny little anomaly is a reason to tear everything apart and start over. So the code has to be crystal clear about what's okay and what's not. And this is how it works. The code gives you a clear pass-fail system. Some flaws are an automatic fail. See that B rating? That means if you find any kind of crack, the weld is immediately rejected. Done. But for other things, the code gets incredibly specific, giving you exact dimensional limits. A little bit of surface porosity might be fine, but only if it's within the strict size limits laid out by the rules. Okay, this brings us to the final hurdle, the grand finale. We've checked the materials, we've checked the fabrication, we've checked all the individual welds. Now it's time to test the integrity of the whole completely assembled piping system under pressure for the very first time. So the system gets put through what's called a hydrostatic leak test, and the pressure is figured out using this formula. Now, don't let the math scare you. The only number you really need to care about on this slide is 1.25. What that means is the system is intentionally pressurized to 25% higher than its maximum design pressure. This isn't just about seeing if it holds, it's about proving it has a massive, built-in safety margin for anything unexpected that might happen down the road. After all of that complex engineering, all the meticulous fabrication, and the rigorous inspection, the final result boils down to something incredibly simple. You hold the system at that super high test pressure, and the goal is clear, non-negotiable, 0 leaks, period. So, as we've seen, this is a complete interlocking system of safety, right? It all starts with verified, tough materials. It demands fabrication that's controlled down to the millimeter. It requires every single critical joint to be inspected against objective rules. Then, the entire system is deliberately overpressurized to prove it can take it. And maybe most importantly, every single one of these steps is documented, creating this unbreakable paper trail that proves quality from start to finish. And that really leaves us with one final thought. Is ASME B31.3, Chapter 9, just a dense, boring book of rules? Or is it something much more, a complete engineered philosophy for managing catastrophic risk, one detail at a time? I think the answer is pretty clear. Thanks for joining me on this deep dive.